Hello. We are going to do our first design exploration of the year where we start looking at other teams' robots and their CAD and going through similar to what we did with our design review where we went through system by system, except here we don't know everything about how they designed their robot. Most of the time I have not looked through the CAD very much. We've seen them play. We may have seen some things on Chief about the robots. But a lot of times there's always cool details that we can find while looking through their CAD, seeing how they designed each individual aspect of the robot. So ideally, we can find things that we like and learn and do better with our robots in the future as we get new and clever ideas from other teams. Tonight, we're looking at Team 6328 Mechanical Advantage. They had a fantastic robot this year. It was rather cool, and so we're going to look through their CAD and see how they did it. So yeah, just like the robots that we did in the design recaps, we'll go mechanism by mechanism, normally starting at the bottom and going up. So kind of looking at their swerve drive, it is very similar to our drivetrain for the two robots that we built this past year, where they have the same swerve modules, the MK4i inverted modules. They are using Neo motors instead of Falcons, but that really doesn't change much in how the modules get built or anything else. They have the little 3D printed corners that we also use. Theirs are a little bit different actually, which is interesting. They go around that center standoff, which might be something we do. So we currently like actually wrap it with the 3D print where we just have like a circle and we press it into it. And so it's the only bolt that goes through our little corner, where they just come in and put two more like standoff features into two outside bolts. But I don't know. Oh, so I wonder if they drill into here. So we had considered that on one of our setups for a couple things. Like this flange is a little bit thin, this like web here in the part. It gets milled out by SDS when they ship it. But you can drill and bolt into that. So they could do something like that. Because this is a threaded hole in the SDS module. So there's a bolt going down into here somehow. I don't know if it goes all the way through. They might just bolt it into the 3D printed part. You could do that if you wanted to. So those, it's a pretty decent. Oh, it's on the other side. There's the hole. So it's a relatively wide hole. It's a .266 hole on the inside here. So what I think they do is this part gets a inserted nut. Yeah, so it has that little like the recess here. So it's probably a heat set insert or a screw expand insert goes into here. And so then they just bolt those in from the top of the module. And so there's nothing supporting the bottom most likely. They could put another insert and drill a hole. That'd be really hard to do right here where it like hits the rib. So they're probably not doing that, at least on this side. But you don't really need to. This doesn't have to be anything all that structural. Just bolting in from the top works pretty well. And then you don't have to deal with you don't have to remove the standoff to take it on and off, which is pretty nice. And you can make this part a little bit simpler to make. It's just a single 3D printed part. That's a little bit easier. We might actually start doing something like this. That saves some time. Because we had some issues with ours breaking and stuff. These would be easier to replace if you just undo those two screws. That is a small feature, but already pretty useful and cool. So what these things do is they help make your frame perimeter flat out to here, so that you can meet all the bumper rules about how close your bumpers have to be to the frame, and how many gaps you can have in things. So these corners just fill out your bumpers a little bit, and they make it much easier to be compliant without having to like change some of your bumper geometry and anything. So they only pushed it out really on one side where they have this plate. They left it small on the other side because they have this, it's fully flat back here. There's no plate mounting here. So they just left it basically flush with the swerve module. So that's pretty easy to do. They did a somewhat similar battery mount to what we normally do. We don't have this rail crossing here, so on our robot we have to have like little standoffs coming off, but having the rail makes it really simple. You're able to put the battery right there and strap across it. Let's see. Yeah, they have some of their other electrical. This is an interesting way to do the Robo Rio. So these little blocks kind of frame it in, and then they have smaller blocks that they screw down on top of it to basically clamp it down. Um, for the most part, we just use VHB tape, like double stick tape on the bottom of ours, and stick it down, and it holds up quite well. We haven't had any issues. But something like this would make it easier if we ever had to swap the Robo Rio. Having to pry up the VHB tape is kind of annoying. Where this clamping setup, you would just undo some screws and you could swap it in and out. So that would make the repair a little bit faster. Most of the time, if we have to swap a Rio, we probably have enough time to either pry it up if we have a long enough to play in matches, or we might just put another one on top of it, plug things in, and go to the match. We normally try to have at least a little bit of weight so we can do that so we're not overweight. And so you can just unplug everything, plug it in on top, and strap it down with VHB or zip ties or whatever else you need to get it to at least stay for a match. Looks like they also had a steel belly pan, either steel or aluminum. Probably most people's this year were steel. 1/8 inch could be steel or aluminum. We could go see if we really wanted to in like weight properties. See if it shows up. 6.7 kilograms. So I'm not sure if that's steel or aluminum still. But either way, it would work. So if you need some extra weight down low, you could make it steel. If not, you can make it aluminum. They have these full circular arcs down here where we have kind of like straight line cutouts. But nothing too different. Where they actually start getting quite a bit different is where they mount their superstructure. And so they build it all off these two main plates on each side that pretty much mounts the whole rest of their superstructure. So their chassis is basically fully separate. So instead of having like that whole mounting rail system or anything that like we did, or mounting in multiple places of the chassis, they just have four rather large mounting plates that build up a support rod on each, or a like 2x1 vertical support, and then the two angled like A-frame supports in between them. Let's see, so they're not too much longer. Yeah, so they're actually pretty small. So this robot's 25 by 25. So it's pretty narrow. Ours were 27 by 24. So we'd have a little bit more room between our swerve modules if we wanted to do something like this. You could have these tubes be angled out a little bit more, so a little bit more angle for support. These plates would get a little bit bigger. And so you could design things in like that. So yeah, so that's the structure of what is their arm supports, but we're going to skip over to their intake. And so this is actually really useful for a lot of swerve drives and a lot of swerve designs. Something like this could help a lot. Because one of the tricks that we talked about on for our off-season robot FM was how do you actually get to mount over the swerve modules is often pretty complicated with the MK4i because you don't have a lot of mounting support in here. There's some teams who will use like nut strip mounted to these bolt holes on top, and then you can mount some plates onto those. And that works a little bit, but then everything's like integrated into the swerve module, so if you ever need to replace the swerve module, you're unbolting parts of your robot off to do that, and even just maintenance and stuff gets a little bit harder as you bolt things to the swerve module. It's always a little bit harder to get in and maintain it, keep it clean. If you need to swap any of the belts or anything, it's a little bit harder, and there's things mounted around it. So these polycarb plates here that they just have mounted to the A-frame are able to just overhang the swerve modules enough to be the pivot for their cube intake. And so this is rather simple. This works pretty well for any game object where you can have this high of a pivot. They didn't need to try to drop it any lower down near the swerve module or anything. It's hard to get too much lower than the swerve module anyway. They can only go a little bit lower if they wanted to. but this lets us have the shaft pretty close to the front of the robot and still reasonably supported by those modules. And it actually, because you have these polycarb plates, you get a little bit of compliance built in that if something does come in and like hit this from the side, these plates are able to bend a little bit just because the polycarb is flexible, more so than aluminum. And so they can take the shock pretty well. They can take the impact. Polycarbonate is very impact resistant. And so you shouldn't have too many issues with something like this breaking. If you wanted to, you could stiffen it up with more standoffs across here. So they only have, in CAD at least, this one, and they just have the hex shaft running straight through it. If you had a standoff a little bit closer, you could make it a little bit stiffer between those as you make the sandwich. Have more standoffs between it. This whole assembly gets a little bit stiffer, which if you started to see too much flex, you could do. It looks like they had another bearing set up here, so this might have been for a different iteration. This might have been for a motor mount of some kind. It's very possible they just designed in a different intake at one point that used another rod or something, so it got left over in CAD, but they just kept it because this intake pivot still worked. But it doesn't look like anything's there, at least in the CAD, that's visible. Let's see. So yeah, so that's how the intake supports the pivot. How it actually works as an intake, from what we can see so far, is something has to power this hex shaft to be able to power it up and down. So they make, oh, that's actually kind of cool. Let's see. So to actually be able to move it on their, I'm guessing on their router, they cut in the hex profile into the tube directly. They have these circle overcuts because when you have a rounded bit on like the router, you have a round cutting bit that's spinning. You can't make the sharp corner of a hex. So they overcut into the corner with an 1/8 inch router, with an 1/8 inch router bit with a CNC bit. They're able to do these overcuts into here. And so this gives space for the hex shaft corners to fit, or the rounded hex shaft corners to fit. And then you can transfer all the torque on all these flat sides to the 6 flat sides of the hex. And so as the hex spins, the arm spins, and you get a really tight, light package because you don't have to have any hub or anything, and you can still just run the 1x1 out to have nice, easy mounting and relatively strong structure compared to just a flat piece of polycarbonate or flat piece of aluminum. The tube gets you a pretty stiff structure out here that's very easy to mount to. You can just bolt or rivet. So cutting in the hex pattern on the router is a pretty clever way to do that. What we don't necessarily know is how they actually power the pivot. So they have to have a motor somewhere to spin this. My best guess and what I believe is happening is this Neo and Max Planetary over here that doesn't seem to be attached to anything else is powering this somehow. So there's either it doesn't quite look like you can fit a belt directly here. So it's possible maybe that this is what that's for. This might be like an idler. So you have a shaft running through here that has a pair of pulleys or sprockets on it. And this shaft runs up to this one, and then this runs down to this. That's a very possible way that they're doing it. They could also have a motor mount somewhere on here that just directly does it, that just didn't get into CAD. A lot of times things like that change throughout the season, so you don't exactly know how teams, how the robot works just from CAD, because not everybody's CAD is fully detailed everywhere. So even though they CAD'd the chain here, we're almost certain just from context clues that something is powering this hex shaft. It just didn't get into CAD, or it's hidden in this version of the model, or something like that. The other part of the intake is the actual roller itself. And so they chose to use a non-brushless motors. They're not using a Neo or a Falcon up here for their intake. They're just using a one of the Andy Mark Redline 775s, which are similar, or in the model at least, which are similar to the 775 Pro motors. These were very common on intakes forever. They're still pretty common on intakes. And the advantage is they don't have any sensor wires, and you don't have to run like the CAN bus out to this or anything. You just have to run power to it, and you can run the power back down to a Spark Max somewhere. And they're just brushed motors, so they don't need any of that advanced logic or anything. You don't get the encoders or the sensors that you get with a brushless motor, but it is a little bit lighter, a little bit easier to package, and there's a little less risk of any of the, you have fewer connectors or wires out here, so you have less risk of them failing and messing up. So a lot of teams will use brush motors if it has to be all the way at the end of the intake, like this design is, where you have the motor gearbox like right above the roller. So when this is deployed, it's going to be pretty far out there. So another robot could run into this, or if you ran it into something exactly right and like bent this bar, you might hit the motor. You may not want to have a Neo or a Falcon out this exposed on your intake. A lot of times you do this just so it stays out of the way, so the cube's going to come up inside it, like on the inside here. And so the cube doesn't ever touch the motor here, where if you put it farther back, the cube might run into it. So it ends up being nice and easy to put out here. You also have a really short belt run. So you have the belt on this pulley here. There would be another pulley that's not in the CAD or not modeled in this version that we're looking at. And so there'd be a pulley here, and you'd have a really short belt. Short belts are great. They are very hard for the belt to have a lot of time to skip, because you can keep tension on them very easily. And the what's the best way to describe this? The amount that it would need to stretch for it to be able to come over the flange is a much higher percentage of the total length of the belt. So it's much, much harder to get it to pop over a flange or to come off of a pulley when you have a short belt compared to when you have a really long belt. If you have a really long belt, every little bit of belt just has to stretch a little bit, and then there's enough room for it to like come over the pulley or to stretch, and it's just harder to keep everything in tension. It's much easier for like the plates to have flex between them, even if it's aluminum. It's still easy for them to get out of alignment just a little bit, and then your distances aren't quite the same. And so it's much more likely for a belt over a long distance to come undone if you don't have other ways to tension it than for a really short belt. So you get some advantages there as well. Ooh, I rotated too much. Okay. It looks like their roller is just a live axle hex roller, so it's relatively easy. They have the 4 bearings, 1, 2, 3, and 4. There'll just be a hex shaft running all the way through it. And then it's like 1.75 OD something. They build a hub of some sort. 2-inch OD. Yeah, so this might be this might be like 1/8 inch wall plastic. It's probably 1/8 inch wall polycarb maybe tube. So 2-inch OD. Could be something else. Could be rubber. But something's probably, if it's polycarb, there's probably something wrapped around it to be able to intake the cubes nicely. And they have some version of a hub that they would put inside of it to attach it to the hex shaft. Normally those are just going to be printed hubs. Some teams who don't have printers would use wheels sometimes. You would find like a hex wheel that fit inside the tube exactly, and then you could just like screw into the wheel through your tube. You can make a roller that way. But nowadays with 3D printers, most teams can just print any hub they need and make it work very well. The last part of the intake is this crossbar. So that's just a standoff here and bolt, and most likely a star nut inside of this tube that they're bolting into. So there's star nuts, they're often used on like parts of a bike sometimes, but you like hammer them into the tube, and it allows you to have a threaded end right in this end of the tube. It's a .196 hole, so that's a number 10 going through. So if they are using a star nut, they're probably using the rev Star nuts, this is probably a 3/4 tube. Yeah, so my guess is this is probably a Rev star nut in here with the Rev, either the Rev 3/4 tube or any other 3/4 aluminum tube. We had some issues with the Rev star nuts where we'd twist them inside if we torqued them too much, so we stopped using them, but other teams have had a lot of success with them, so they definitely work, and they allow for a very easy and light, strong standoff, basically going across your whole intake to give this thing structure, so this whole part doesn't rotate, and keeps these both ends in parallel so that they move up and down nicely together. And it also works as the first thing to hit. If you drive this into another robot or anything, you're not running into your roller. You break this bar first, and it's relatively easy to replace if you bend this, compared to having to replace your whole roller and hex shaft and everything else. So having a kind of front bar to take the impact of another robot running into you or you running into another robot can be really helpful on intakes. All right. We talked more than enough about the intake. Let's move up. I think that's most everything. So what do they do here? So they have a gearbox that gives that has 2 Neos on it. So we're going to ignore this one because we believe that's for the pivot on the arm and for the intake. And so these 2 Neo motors here are driving that gear. Let's see if I can do something useful here. We're going to go in to Onshape and we're going to make ourselves a section view. So I'm going to split it out. I'm going to go do I want to go the other way? There we go. Back it up to where we can get the gears. Okay. All right, so in there we can basically cut away part of the robot and we can get in to see the gearbox. So some of these things we can see, like there's just like an issue with the model. The power distribution hub is not actually here. It's almost certainly just slid over a little bit. Maybe it's on the other side away from the gearbox. That's probably the best guess is it's just over here. It just got modeled, flipped around. It happens. Okay, so the way a gearbox like this works is they're basically just trying to get the 2 motors to spin at a much lower speed and have a lot more torque, rotational force, to be able to move the arm in a very controlled manner. So they start with 2 really small gears, one on each motor, that are called pinions. Except I'm doing section view still, which is not what I want to do. Let me check in that. There we go. Okay, so they have pinions here and here. We can look in the arm real fast and we can see exactly what it is, and we could calculate the whole ratio of this gearbox if we wanted to. So this is a 12-tooth gear. There's another one here. They're driving this larger gear, this 52-tooth gear. And so we've talked about this a couple times, but it's always good to go over again. Basic gear ratios mean that as this 12-tooth gear spins and this 52-tooth gear spins, for every 52 over 12 times that this one spins, that one spins. It's a little over 4, right? Because 4 to 1 would be 48 to 12. This is 52 to 12. So for every like 4 plus a little bit that this small gear spins, this big gear is going to spin once. So it's slowed down more than 4x from these. And then we gear it down even further because on these 2 share the same shaft, so they're spinning at the exact same speed. And we go down from this gear, which is an 18-tooth, and it's driving another 52. So we gear down even more, 18 to 52. And then there's a whole nother gear set. So this is what we call a it's actually 4 because there's even another gear set we're going to see. So we have the first gear reduction here. We have the second stage here, this small one to this big one. The third stage is back here where we go 18 to 52 again. So that's part of the design here is they used all the same gear teeth, which worked really well. So they went 12 to 52, 18 to 52, then 18 to 52 again. That lets you buy the same gear over and over again. So you have spares. It lets you do all your math easily because you're just typing the same number over again. And if you can package it all, it works pretty nicely in a setup like this. So that's gear stage 3 going 18 to 52 again. So they're making it go even slower, right? And all these multiply together. So if this is 4 to 1, we'll call this 3 to 1. You get something closer, it's above 12 to 1. We could do all the exact math. And then you get something even higher over 36 to 1. And then they come out on the last stage here and go 24 to 68. So there's a 4-stage gearbox to drive this arm, starting at those small gears on the motor and going through each stage to get a lot of gear reduction to be able to move the arm smoothly. Similarly, you can do things like using the max planetary gearboxes. That's what we did on our arm on FM. So those gearboxes were set up with 2 5 to 1 stages in each one. So there's like 25 to 1 in the gearbox. And then we had a chain and sprocket that let us go another 4 to 1 for overall 100 to 1 reduction on our arms. These ones are probably a little bit bigger than that once you account for the final chain reduction here. So you get this final gear reduction, like 4 stages of gears. They mount into this rather cool max spline assembly here to actually power their arm. And so the cutaway actually helps a lot here so we can see exactly what's going on. They have some spacers, but they have max spline sprockets and max spline gears. Some other, what they do, they've made some 3D printed spacers probably. Yeah, so it's just a big 3D printed max spline pattern spacer here. Goes over and clamps this side of the gear nicely in case anything ran into it or something. I don't think, yeah, they're not bolting into it. It doesn't look like they have bolt holes there. And they just have a few more of these spacers that they printed out to keep the spacing along the max spline to go to the other side for the other sprocket. So both these sprockets are driving at the same time to keep the sides in sync, which is really important here because there's not a crossbar here since the upper arm has to swing through. If these chains get off, this whole assembly can angle away from itself and not be clocked at the exact same. So like it may not line up together if the chains get off. So you want to make sure that they're completely synced down at the bottom by having them run on this large max spline shaft. What are we gonna do? I'm gonna turn off so I can edit section view real fast. Oh, nope. I edited section view not the way I wanted to do it. To come back here. Let's see. Okay. So, oh yeah, you can only see it for a little bit. So they ended up putting, let's hide parts and see it. So inside the max spline, it looks like they just put a rod and bushing. So this is a, yeah, so this is a full bushing that was made somehow. So yeah, so this is a McMaster part. So the max spline tube can spin on this bushing because the tube through the center is running all the way through. And so that was the part I wasn't sure about. And so we can load it as we investigate. Yeah, so they have just a solid rod here. 3/4 inch solid rod that they probably drilled and tapped. Yeah, so it's probably fully solid. They drilled and tapped the ends. Then they put these bushings on top of that. Get it where it's just the bushing. And so then this bushing goes on top of that. and the max spline tube spins there. And so these are basically fully clamping that plate that I hid. So that gets you a really strong shaft going all the way across the robot that's not spinning at all. Then you have those two bushings on top, and you get the max spline splinting on top of those. So depending on what has this slightly lower coefficient of friction, probably the max spline is going to spin on the bushing, and the bushing will stay still. But it could go the other way. The max spline could spin with the bushing, and the bushing can spin on the shaft below it. The nice advantage of that is if you remove those two bolts, so if you just take this bolt out and the one over on this side, the whole shaft can just come out. So this whole long shaft here can just come out of the robot very easily. And so you could replace it if you needed to, or if you needed to work on it, it'd be very easy to work on. Because it's not actually going through these plates at all. There's no bearings or bushings in these plates to hold the shaft in. We're having to slide it out from either end. It makes it really easy to take on and off when you just bolt in through the ends like that. Okay, so coming up to the top of their like A-frame structure and their arm mounts, I missed one thing down on intake, and I just saw it up there, so I'm going to go look at it again. Over here on their intake, they have a rev through bore encoder. So this lets them directly sense the position of this hex shaft. So as this moves up and down, they can know the exact position of it and control it really nicely to go where it is. They also seemed like they milled the face of this down a little bit so that it could spin easily inside these two plates that only have a 1-inch gap in them. So I missed that the first time. That's why we do these things though. So you can see here, they basically like on their, most likely on their router, they were able to mill this little bit of a bearing boss to keep it exactly at 1 inch and act like a spacer. And then the rest of it, they milled just a little bit flat. So they made it like a 32nd of an inch down so that it doesn't rub anywhere else along here, so that this face and this face don't rub each other. They milled it all off, likely on a CNC mill or a CNC router. So that's fun. Okay. Back up here. So they make some rather large plates to hold their whole arm, which makes a lot of sense. This is their whole scoring mechanism. We want these big 0.226, so probably 1/4 inch aluminum plates that got routed out or milled out to have the mounting holes in for the 3 different tubes, and then some weight lightning as well, as you can see in here. And then these are how they support the dead axle shafts that the arm is spinning on. So in here, let's see if we can see how this all works. Hide this a little bit. There we go. So we can find the bearing. And so they have a bearing here. And so that's what's actually, the arm is spinning on top of this bearing. So the shaft here doesn't spin. And so that plate is supporting the bearing nicely. And so most of the load from the whole arm is running through this plate and the bearing. And there's probably one on the opposite side that is similar. Yep, so you have another one here and the bearing on this side. So you have 2 bearings and those 2 aluminum plates. And they're all clamped together with some 3D printed stuff going on. So you have some cool 3D printed stuff like this. You can isolate that. So you have this like arm here, or this inside part of the arm that lets them put these large aluminum plates in that actually do most of the connecting work. Right, so they insert into that tube and they bolt through it. So this big tube here that's going to be their arm is bolted to this pivot really rigidly, can't move anywhere else, and it's attached to everything. And then they do the same thing out with the sprocket, where they bolt the sprocket through all of those plates and everything and attach it so that as that sprocket turns, these arms have to turn as well. We can see what that sprocket looks like if we isolate it. So yeah, so it looks like they were just using the rev sprocket, I believe. I think that whole pattern comes on it, if I'm not mistaken. The 48 tooth red sprocket, it might have at least some of these outer holes. I don't know if it has all of them in the default pattern, but I think it might. So they could be ready to go. They might also had to drilled some of them, but maybe not. Those might come stock. Either way, you could drill them if you needed to, or use them if they already exist. But anyway, having bolts towards the outside gives them a much longer lever arm from the pivot, so you have more control. You're less likely to break any of the bolts or anything like that. And then they attach down here the gear that just lets them have another absolute encoder or through-bar encoder, so they can know where their arm is, even if the motor state changes. They don't have to just like zero it at the start and know the position like we did with FM. They can boot it up in any position, and this encoder can tell them where the arm is, and so they're good to just go back into their home states and into their positions using this encoder to get data from it. There is another really cool thing in here that I just noticed that is hard to see. So they are using what appear to be like mite bites, or maybe they're custom mite bites. No, they look like yeah, they're fixture clamps. Okay, so this is actually really clever that I did not know before I opened this up. These fixture clamp bolts here, let me see if I can get which one I want to do, a little bit better view of this. There we go. Okay, so these bolts here are the same type of bolts that we use on our CNC router tube clamp to be able to clamp the tubes down. So they have this like what's called an eccentric shape to them. That's why like the center of this bolt isn't centered on the bolt head, and so it looks wrong. Like it looks like it's like manufactured wrong, but it's built that way so that as you turn and tighten this bolt, you change the distance that this hex is away from these plates here. And so you can do that to be able to push the mounting tubes here of the arm out away and be able to tension the chain somehow. So you can change the position of that tube, and then you can change the position of the chain. And so you can make the chain as tight as you need to. But I'm not entirely sure which direction they're able to do that in. So let's see, by tensioning that, they're not changing much. What are they changing? So the bearings not slip into there. Let's see. Oh yeah, it looks like that hole is just larger. Is there anything in there? No, it looks like that's just a semi-large hole. And that lets them change the location a little bit. You can see it's not quite the perfect shape we'd expect. Well, I'm not entirely sure how they're doing this one, but that's most likely what it's for, but I might have got that wrong if that's not how that works. So they come off and they're able to cross differently, but they can't do too much. What am I missing here? Those are round and bolted there. So you shouldn't be able to move it too much just by moving those clamp blocks, because the other holes are still concentric, it looks like. Yeah, those are concentric. So as you put a bolt through that, you're going to tighten it down pretty tightly. Oh, I know what it's doing, I think. So it's pushing against... So it's pushing against this tube, possibly? Nope, those don't touch. That's not what it's doing. So you can tension this, but it would push it down, not up. Because the chain tension is going to be pulling this down. Okay, now I get it. Okay. So the chain tension here is going to be pushing this down. And I think because it's cantilevered, right? So it's cantilevered out here and all the force is coming down this way. As you push this side down more, right? As if we were like pull this blue tube down really hard, it would angle this side up and give you chain tension. I think that's what's happening. I'm not 100% sure. They might have answered in their build thread somewhere. I don't think I ever saw them talk about this. But that would make some sense that as you pull down either on this one or on this one, especially if you make them opposite, if you pull down here and raise there, you would definitely get a motion upwards here to push away from the chain tension. It also might just be for some sort of alignment. I'm not entirely sure how they do that. But we can ignore that for now. The rest of the arm setup is a little bit easier to see. So they have the large tube that they use as their pivot. So they want something really thick so that it doesn't bend. Since it's all cantilevered here, it's not supported on this side. And it's cantilevered a pretty good ways out, right? You have this whole unsupported span here before you actually get to the arm. You need something pretty thick so it doesn't bend at all when you have that much motion and force going through it as they're trying to move from different scoring positions. You wouldn't want that to bend. That would make the robot much, much worse. And so that same thing is happening over on the other side, just without the analog encoder. And so you can see that same setup here with a spacer and all the bolts and everything. So a lot of the bolts aren't actually catted over on this side. They were catted on that side, which makes sense if you're worried about clearance somewhere. Just doing one set is easier than doing both if it's a mirrored assembly. And then it definitely loads faster and everything too, without having to have bolts on both sides. Okay, so this joint is what's powering this first joint of the arm and moving it around, and it's able to swing through and go up or down. And then they also have another motor assembly here and another custom gearbox that's driving gear sets, kind of like the one that's down low. Has a plate that drives through the gearbox over to this side, and we get a sprocket here that comes up and powers this sprocket to actually move the second joint of the arm in and out. I don't see what this sprocket is for. It doesn't seem like it has a counterpart currently, but it's very possible it did. I could imagine that this was for a through-bore encoder at some point. Maybe they were doing the encoding down here, but then they decided to switch to doing it up here. Could have some other use that I just don't know about, but it doesn't seem like there's too many context clues for what that one would be. But the main driving here is you have a sprocket here and here. They did a similar thing again to be able to put tension in. So I'm still not entirely sure how they're using that. That may be something to research, but they have like these mic blocks again, which seems like a pretty cool way to do it. Mostly because it allows you to get that motion that you need up and down here without having to have any sort of bolt in the end of anything or like going in the other plane. So a lot of times teams will have to figure out a way to put a bolt like almost in this direction to like pull on this tube to pull it back up and tension the chain. That's pretty hard to be able to mill that assembly and things and get it in there. It can be pretty tricky to make, where if you can do everything just in the side of the tube, like they're able to do, or into a plate, that's a lot easier for a lot of teams to manufacture. They have a nice big sprocket up here to power this. So this one it's a configurable sprocket, so they might have made it or bought it. They also have a giant hole in it that may be for like a wire path or something to go through. I'm not entirely sure what the big hole would be for since there's only one. And then it's likely bolted into something like this hub. Yep, so you see the holes there, so it's bolted through this printed spacer and then bolted all the way through these same style arm mounting plates again that they use down here. It looks like they're almost the same part 15, part 22. So they say they're different parts, they probably are, but they're very, very similar design styles. And so you could imagine you could route all of those using a similar bearing and shaft and everything else. I think that might have been a different one. Let's see, it's not shaft. Yeah, so that is the same. So that's a different different OD shaft. Let's see what OD down here. Oh no, those are the same. Okay, so yeah, so that's the same shaft diameter, but a little bit thinner wall. Since it's going all the way across, it has more support. It doesn't need to necessarily be as thick as this one did. It also has less weight it's supporting since it's only supporting the rest of its arm. It's not having to support these two arms and the rest of the intake and or the rest of the arm and everything. Okay, another absolute encoder so they know where this arm is. And then we move down to the final part of the arm and the intake itself. So up here they have a Neonimax planetary plus a sprocket. That sprocket's driving a chain way down here. It looks like this got inverted somehow. So in CAD, the sprocket's on this side and the motor and gearbox are on this side, the sprocket's over here on the left. It's very likely one of these two things is flipped around on the real robot so that that sprocket can connect to that sprocket easily. It doesn't matter if it's perfect in CAD, as long as you know you can flip it over and mount it in real life over here, that's fine, or have the intake flip around and have the sprocket on that side. Whatever works. And so a lot of times the CADs aren't perfectly detailed to real life. You just make sure that your spacing and everything is right, and if you know it's symmetric, you can mount it whichever way you want when you actually build it. So this pivot is doing our intake position, and so they have another rev through bore encoder. This gap here leads me to believe there's probably another like gear on this and a gear on the rev through bore encoder to let them see the position of the wrist as it's swinging around. So you have to control the shoulder, elbow, and wrist on this arm to keep, to know exactly where the game piece is, to drop down and get your cone intakes or get the cones off the shelf, or to pull cubes out of the cube intake. You have to be able to position all three of those really well. And then the intake itself is pretty simple. There's a Neo 550 motor, so these really tiny brushless motor from Rev going into the ultraplanetary gearbox, which are the similar gearboxes that they use in, or the same gearboxes that they often use in FTC. That comes up and powers a gear here that also powers a gear here. So this is the same style that we did on FM, where you have the two gears that let you reverse the directions. And so you have these two pulleys that then power your set of back wheels and your set of front wheels. And this same style intake has worked well for a lot of people to be able to grab cubes in the front one and then pinch cones in the back one. And that largely finishes off the mechanical details of their robot. The last thing I want to hit before we end is they also have some of the best programming and autonomous modes in the world, and one of the ways they did that was they designed these cool camera mounts that ended up being their swerve encoder covers. So like the can coder is here, And so they designed these to be able to cover those and protect them, but also mount their cameras. So they would have cameras mounted on these faces. And they were set up so that they could be almost always able to see April tags whenever they could. So they were able to do a lot of localization, which means they just knew where the robot was on the field almost every time during the match. And from there, they could do a lot of the path generation to automatically have the robot drive in and go to the specific scoring node they wanted to. It made their autos very, very accurate. So there's another one back over here. And so they had to had them all to be just out of the way, right? So they didn't want it to be in the way of where the intake was. They wanted the camera to have a good view. The intake comes up and the camera can still see through it. And so these 4 cameras are always doing a good job of trying to be able to see an April tag, even if they're at some sort of weird angle to the April tagging thing in the scoring grid. They're trying to always be able to see one. And they can do really nice software that way. Oh. Okay. I think that pretty much covers their robot. Yeah, they had a very successful season with this triple axis arm, cube intake, and again, some very nicely done software to get them to have very reliable autonomous modes and fast scoring throughout the match.